paper machine, we're going to draw what you're going to see out there. Number one, on a paper machine, you're going to have a camera. And then on that, you're going to have some sort of LED next to that camera. It's going to be on a paper machine. All right. And then another item, you're going to have steam. All right. And then you're going to have what we call an ROI. Some people call that a region of interest. Some people call that a scene. Another way to look at that is your FOV, your field of view. What is the camera looking at? And then you're going to have the result of these 5 things above it. What happens when you combine all of that into that nice little sandbox? And then after that, you're going to have the ECS answer to what we know. And then under that, there are 7 elements to what we do in order to deal with what we're about to draw out. That is cameras, lights, steam, paper machine, looking at something. So here's your camera. And here's your LED. The camera has a little sensor on that camera, CMOS sensor. And then traditionally, this is just maybe a pickup suction roll on the front side of your paper machine. You've got your felt right here, and you got your paper right there. And then you have steam. You've got something that is surrounding that right there. And inside that steam is your field of view, your scene. It's what you want to look at, your ROI. It's right here. Boom. So here's your camera looking at that with its field of view, and then here's your LED doing the same thing. So what happens when you use a traditional LED? Well, energy comes out, and the minute it hits that water vapor, it scatters. And it bounces that energy right back to the camera CMOS sensor, presenting it with a wall of white energy. You do not see what's inside of the steam. You do not see the important part of the image. All you see is white steam. So in terms of the ECS answer, number 1 out of the 7, you have to use near NIR. What does that do? Well, NIR, at the wavelength that we use, which is still sensitive to the camera sensor, is a longer wavelength of light. So it's able to penetrate through the water vapor in order to hit my region of interest or my scene, and then bounce back so it can be received by the sensor. But no normal NIR light is going to work, because even though it has the advantage of the longer wavelength, the challenge is I need to produce enough NIR in a certain way that it's able to make it through the steam, not stop at the steam, get here, and then bounce back again. So the second part of what we've got to figure out is the power. And the power of an LED is divided into 2 distinct places. Number 1, I'm going to talk about how we hammer drive the LED. It's called strobing, but it's a hammer drive. And then number 2, the power that we can provide through that hammer drive. So let's think of this. This right here on the x-axis is time. My y-axis, we'll call that energy or power. Turns out that when that camera takes its first image, let's say right here, that's 1/60 of a second. And then later, if it's a 60 frame per second frame or camera, could be 100, could be even more than that. But for this example, we'll say it's 60 frames per second. It's going to take another image. And then at 3/60 of a second, it'll take another image. What the camera's actually doing, though, is the sensor, or the chip right there, is only on for between 50 and 100 microseconds. And then what happens after that? It actually turns off. Then it turns back on again a 60th of a second later for 50 to 100 microseconds. And does the same thing, turns off. And does the same thing right here. So when it turns off for about 16,500 microseconds. So the on time with the camera with the correct shutter speed or exposure is like less than 1% of the time. So then consider the LED or the light source that goes with that. Traditional LED systems called constant on, they stay right here. They're on all the time. That's problematic because it generates heat, and it also wastes energy because the light is on when the camera is not on. So what you want to do is you want to develop a system where the LED turns on at the exact same time, very precise timing that the camera is taking the picture. And not only do we want to turn it on, we want to blast that LED with a tremendous amount, magnitudes more than you would ever do with constant on. So we talk about making silos versus shopping malls. And the amount of energy is hundreds of times more that we can get because we're only blasting that LED for a couple and again, 50 to 100 microseconds, and then turning the LED off. That creates the amount of energy that we need to get through that steam. The other element is the way we construct the LED. This is a picture here, or not a picture. This is the actual chip on board that we use. 256 LEDs put on this board right here. Notice there are no reflectors on this board. This is just the chip right here. That has two distinct advantages as well. It's the way we focus the energy without having the individual reflectors on the LED. That allows us to mask the LEDs in one very, very tight area, then use a different technology called a Fresnel in order to focus the energy. And then number two, it's another thing you don't notice on this. There are no electronics on this chip whatsoever. So this is the LED built into the body right here. Notice the Fresnel lens right here. Fresnel lens is the technology they use in lighthouses. That is a completely even way to distribute the energy. And the way you focus it, it's the distance away from the chip or the chip on board that makes it a wide angle or a more narrow angle. But within that wide or narrow, it's perfectly even lighting. And we're going to show some examples of when you don't use Fresnel lighting technology, what that does to the camera's ability to collect resolution. In order, though, to have and use Fresnels, you can't use individual LEDs all over a board like a pancake. You have to concentrate that energy as tightly as you can. And the fact that it has no electronics means that this light head can survive with no air inside your dryer section up to 220 degrees Fahrenheit. There's nothing to burn. The driver and the power supply are remotely located. So this can live in that environment without air. So many times we go to paper mills, the light's out. You know why the light is out? Somebody disconnected the air. Somebody disconnected the water. And they don't know until days or weeks or months later of why that has occurred. We want to reduce that failure point by developing something that can withstand the environment, even in less than ideal circumstances. Another one, notice the front face. It's completely smooth for silicate glass so that it can be wiped down. There's no bevel on the glass. And also, if you want a water fall on this, you can clean the light that way as well. So you got to realize it's not just the technology. It's the way you house the technology. It's the way that you deliver the technology. It's also the way that you have to make the technology survive in these conditions in the paper mill. That's the legs of the kitchen stool. Any one of those goes out, the system fails, does not provide the uptime that we need to get the resolution to the operators. Therefore, operator utilization goes down. So one last point on this one. We've already talked about if you can answer all of these things and get all of this right, there's still another significant challenge in the paper industry that is above the steam, above the temperature, above the resolution that we provide. And this one is also specific to NIR. Turns out that NIR energy is monochromatic. We use a wavelength of about 850 nanometers. White light is not monochromatic. It has all of the visible light that we can see inside of what it projects out. So what happens when you take a monochromatic light source, send it up to a brown board, and then that reflects back to a black and white camera? What happens is that brown board, because it's being hit by monochromatic light, then bounced back to the black and white camera, appears white to the chip. Creates a much higher degree of contrast, which then means that images that would normally be dark with a very good, maybe, even if you get the strobing right, you get the chip right, you get the Fresnel light right, and you use a white light, you're not going to get the performance that you're going to get out of a near infrared, given the same amount of energy and the same setup. There's one example we'll show you later on here, and that is in a basement section where you may be up to 30 feet away from what you're trying to look at, and you may be looking at 280, 300 inches wide sheet. Traditional systems have multiple LEDs down there, just a whole bunch of electronics already and roasting and dying. With the NIR technology, examples will show you, one light was able and is able to give you enough of that correct energy so that the camera, most importantly, can operate at the correct shutter, correct depth of field, and correct contrast. Anybody can put a camera in a closet and give you pixels. It doesn't matter. It's the quantity of it's not the quantity, rather, it's the quality of what we give you. So we want to give you both. Quality is defined by depth of field, shutter speed, which is stop action clarity, and then lastly, contrast. Contrast being the darks look dark and the brights look brighter. The other problem that you get into if you don't have the right light and we talked about this before, what do cameras do when they operate in poor conditions, when they are light starved? And I'll show you the examples, but to talk about it here, there's 3 distinct things happen when you don't have enough light. You can still produce an image. You can have a 3 million pixel image of nothing but blur because the light is not there. Number one, there's no contrast because you have to bump up the gain, which is an artificial aspect of what you do. Signal to noise ratio is then suffered because you have the noise, more noise than you do have signal. So the image quality goes down significantly. Number two, you have no depth of field. That means that cameras on the outside of the machine, there's no way to get focus on the middle or even maybe the back edge if there's one position versus what's on the front edge because your iris is wide open and you cannot get focus. If you can't get focus on the item, what do you think that dot or that defect or that blemish is going to look like? Well, you're not going to see it. Operators aren't going to see it. Your vision system isn't going to see it, whether it's a web inspection system or whether it's a proactive sheet condition alarm. It's like it was never there. And it gets worse. The third thing is that if you don't have shutter, then it's going to be a blurry mess. It's going to be a blurred image of a blurry moving object because the sensor isn't turning off and on fast enough so that the motion or the defect actually moves while the camera sensor is on. Like if you were to swing a golf club and you took a picture using 1/60th of a second technology, you wouldn't even see the end of the golf club. It would just be a blur for 12 to 24 inches, like it wasn't even there.